Professor, will the Laplace transform work? Let's say in like the homework in 5.2, does it work on those types of problems?
Yeah.
Okay.
I mean, because all of those can be written as second order problems, second order single equations.
Okay.
So yeah, you could use it on those. All right. So now we're on 7.2. So now we're going to get into the details. Now, this is probably not very fun for you to do. And there are some problems in this section. Many of you have already started. And if you use the table, it's super easy. And so I saw many of you already did a bunch of the problems, but make sure you use the table. I'm sorry, make sure to not use the table, at least when we start, right? I want you to do it by definition. So in fact, you're going to have a question on your final that involves doing it by definition. So make sure you do that, because you won't get credit for either one if you don't submit your work and you don't show the limits that we're going to do. It's not too bad. It just takes a little careful algebra, but it's not too bad. All right, so 7.2. So the definition. Yeah, so in this section, we're going to discuss the definition. We're also going to discuss the linearity of the transform. And then we're going to see what conditions are necessary to ensure that a function has a Laplace transform. Not every function has a Laplace transform. And at the very end of this section, which I'll make a separate video for if you're welcome to stick around, but we'll just kind of see if we can build some intuition on it. Also, we're going to talk about something called complex analysis. So if you guys go on and take it, especially you engineers and electrical engineers, you might want to see this because it might help you with something maybe in a future class. But yeah, it's up to you. All right, so here's our definition. So the first thing to know is that we're dealing with a function in the t-domain. We're starting with the function in the t-domain. The next thing to know is we're not considering negative values of time. And this is typically what would happen in the engineering world, right? You have a point in time that you start at and you go off to infinity, right? In positive time. So the Laplace transform, sometimes called the LT of that little function f, is the function big F defined as follows, right? So I already showed this to you. But if you think about what you're doing, all you're doing is you're taking your input function and you're just multiplying it times e to the negative st. That's it. So whatever function you give me, just multiply it times e to the negative st. All right, and so long as the improper integral exists, then the Laplace transform is valid. It's nice to have notation for operators, like a Laplace operator that tells us to do something to something, kind of like we have the differential operator, right? So we use this kind of script L to designate the Laplace operator. So if you take a function and you apply L or the Laplace transform operator to it, that is what you get. You get the transform. All right, we already mentioned this in the last section, but remember, this is an improper integral. To evaluate an improper integral, we turn the integral into a definite integral and then let n go to infinity. And like I said earlier, the t's are just going to disappear here. Once you evaluate the integral, you let n go to infinity, and all of a sudden you just have a function of s. All right, so it's important to kind of step back and look at the bigger picture. The Laplace operator is a transformational operator, and a transformational operator is an operator that takes a function to a function. That's very different than a normal function. You know, if I give you a function like, let's say, let's look at the input one. F of t equals t squared. That's taking a real number to a real number, right? So the functions we've been working with since algebra, you pump in a real number and then it outputs a real number, right? But the Laplace operator is a completely different type of animal, because what it does is it takes in an entire function and maps it or transforms it to another entire function. So we've actually worked with these before. The differential operator is a transformational operator. If you start with a function, let's say of x, and you apply the differential operator to it, it pops out a new function that's also a function of x, mapping a function to another function. So the Laplace operator is also a transformational operator. It maps a function to a function. So it takes this function little f and maps it to this other function capital F, right? But there's one key distinction here, and that's that we're changing domains as well, right? So up here with the differential operator, we stayed in the X domain or the real domain, right? But here what we're doing is we're moving from the time, it's reals, right? Time domain basically to the S domain, which is also known as the frequency or Laplace domain. It turns out that the S domain is a little funky, and we're not going to get into it unless you want to stay with me towards the end of class and discuss the, the optional stuff. But the S domain is a complex domain. Complex numbers. Do you remember these from algebra? Okay, so I'm sure you haven't worked with these for a while. I don't really know how they don't really come up much in calculus. So, but do you remember how to graph a complex number? You graph it on it's called the complex plane, and then you have a real axis and imaginary axis. If you wanted to graph like, I don't know, 1 plus 3i, you would move 1 on the real axis and 3 on the in the y-axis. So, and that you could plot, and essentially complex numbers are 2-dimensional and real numbers are 1-dimensional. Okay, but for right now, we don't really have to worry about that. We're just going to kind of pretend like they're real numbers, because it turns out it doesn't really make a difference until you want to really understand it, which is what we're going to talk about at the very end of class if you're interested in. Okay, so let's look at an example. All right, so let's start with this function. There's a function in the t domain. It's the one function. It turns on at t equals 0. We always assume we're dealing from 0 to infinity for the domain. Let's find the Laplace transform. Let's hope it has one. So the Laplace transform is given right there. You just take the function and you just multiply it times e to the negative st, and you take the improper integral from 0 to infinity. I'm going to hand wave over a bunch of this, but you guys are responsible for doing this in your homework and on the test. So you definitely want to learn this. I'll walk you through some of them, but not all of them. It's too boring. Okay, so this guy on the inside. Okay, so let's say we want to evaluate this definite integral. What method of integration do we use to get from this step to this step? The variable's t, right? S is a constant as far as the integral is concerned. Probably the first type of integration we ever learned, which is substitution, right? Let u be negative st. Okay. All right. So you guys can evaluate that, do that in your work. Then you're going to evaluate it at n and 0, subtract. And then we get to this point and we're kind of stuck a little bit. Okay. So let's pause right there. And now what we're going to do is we're going to, let's see, we're in the S domain, but we're kind of treating it like the reals for right now. Let's break the reals up into 3 different parts. We're going to look at 0, and then we're going to look less than 0, and then we'll look greater than 0, and that'll cover all possibilities. So first of all, let's say S is equal to 0. We have an issue. If S equals 0, then these denominators are 0, which means the whole thing doesn't even make sense. So S is definitely not in the domain of the transform. We have to exclude that. What about S less than 0? Well, if S is less than 0, we also have a problem here. Because if S is less than 0, the negative S will be positive. And what will happen is you have e raised to a number that's getting very, very large. And that's just going to blow up to infinity. So this causes this whole thing to blow up to infinity, which means the whole thing is worthless. Okay. Now, the part that works is this one, when S is greater than 0. If S is greater than 0, then the exponent there goes to negative infinity. And that means that this term right here goes to 0. And what you're left with is 1 over S. That okay? All right. Yeah, so what that means is we've got our first Laplace transform successfully calculated. We figured out that the Laplace transform of the one function, which is a function of s, so I'll put in that for right now, is 1 over s, and it's valid so long as s is greater than 0. Now, the thing is, it gets really messy with the notation. So what we typically do is we drop the function notation, and we'll just write it that way. Is that okay with you guys? It's just easier to see. I mean, we all know we're in the S domain, so just make sure you remember that. All right, so are there any questions so far on this one? Okay. All right, so let's build our way up. By the way, we're building the table right now, the table of Laplace transforms. So we're just going to do some of them, and then you can do the other ones on your own if you like. Okay, let's take a look at this function. This is in the t domain. Remember, all of these turn on at t equals 0. So what we'll do is we'll just take it and we'll plug it into our definition of the transform. All right, now you probably want to simplify this a little bit. They have the same base, so we add their exponents like so. And I factored out a t as well. All right, it's an improper integral, so I'll change it to the limit as n goes to infinity of this definite integral. And then we'll evaluate we'll find the antiderivative of that guy. And once again, that's just a simple substitution. Let u equal a minus s times t. Okay, and then once you get there, you're going to evaluate n in 0, subtract, and now we're kind of stuck again. So let's break the domain down in parts. Okay, there's 3 cases to consider, right? For real numbers, we're assuming s is real. Let's break this apart at the point s equals a. So we'll do s less than a, we'll do s greater than a, and then s equals a. Let's start with s equals a. Clearly, s can't equal a, right? You can't divide by 0. That's going to destroy the whole thing. So that's not in our domain. If s is less than a, we also have an issue because of this guy right there. Because if s is less than a, then that means a minus s is positive. And that means e to the positive n, that's just going to go off to infinity. And if that term goes off to infinity, the whole thing has no chance at existing. All right, so the last case, the one that works, is s greater than a. So if s is greater than a, then that s right there is bigger than that a, which forces a minus s to be negative. So now you have an exponent on e, which is going to negative infinity. And that means that this whole thing is going to go, or at least this part is going to go to 0. And then you'll be left with negative 1 over a minus s. Pushing the negative through, we have our transform. And keep in mind, it's only valid when s is greater than a. And notice we dropped the function notation there, the s. Is that okay? All right. Now, one of the things you're going to notice with transforms as we develop them, a lot of these are generalizations of previous transforms. For example, this is a generalization of the transform in example 1. Look, if we take this rule, and let's say we choose a equals 0. So plug in a 0 there, and a 0 there, and a 0 there. Then what happens is you have e to the 0t. Well, that's just 1. And then 1 over s. That's the same rule that we got in example 1. So what we've done is we've extended the rule for example 1. So if you had to choose one to take with you, this one's more powerful because it takes care of the rule we did in example 1. That makes sense? Okay. All right, let's do some sinusoids. All right, let's take the Laplace transform of sine bt. So once again, we'll just plug it into the transform. Remember, every time you multiply by the same thing, e to the negative st. not much we can do there as far as simplifying. So let's switch it over to the limit of a definite integral. And now this part is a little complicated. The question is, how do we go from right there? How do you find an antiderivative of that guy? What method do you think you're going to use?
By parts?
Yeah, there's going to be a by parts problem. I'm not that mean. I'm not going to make you do it. Okay. But you can do it. You could use a table in the back of the book. You can use computer software or whatever, but I won't make you do that. But you could, and that's what you would get. And then you would evaluate the endpoint 0 and n, and then subtract, and this is what you get. And then we'll have to pause right there. And then we'll go back to the domain of S to see where this thing is valid. So let's split this up at 0. So we'll look S equal to 0, and then we'll do less than 0 and greater than 0. That covers the entire, all real numbers. Okay, so let's say S is equal to 0. Let's look inside of our limit. Well, if S is equal to 0, then this guy drops out. This guy drops out. This guy turns into a 1, right? This guy drops out. So it looks like what we're left with is b over b squared, which is 1 over b. And we've got, oops, there's a b over, yeah, there's another b over b squared. So that's 1 over b cosine bn. Is that okay? Okay, now, if you try taking this limit, there's the problem. There's no problem here. You can take the limit of a constant. It doesn't move. The problem is right here. More specifically, it's the cosine. Yeah, this thing just keeps bouncing forever. There's no damping there. 1 over b is just a fixed number. So it just keeps doing this. So as you take the limit, as t goes to infinity, it just keeps oscillating back and forth between negative 1 over b and positive 1 over b. So it's not really going to approach anything. So it doesn't converge. So that means that S equals 0 can't be in the domain of our transform. Okay, let's try less than 0. That's also a problem too, because if S is less than 0, then what happens? Let's see, that guy becomes positive. So then you have e to an exponent that's going to positive infinity, which makes this thing blow up. And if you have even one thing blow up in one of these things, it makes the whole thing worthless. Unless they maybe counteract each other, if you remember indeterminate forms like infinity minus infinity, that kind of stuff from Calc 1, but we're not dealing with that. All right, so the only case left is S greater than 0. So S greater than 0, I think we're okay. This guy's going to go to 0. So let's see, we can put a 0 there, which actually forces the whole thing to go to 0 because it's a coefficient. So this is what we're left with. And that's the transform. Okay, so the Laplace transform of sine bt is b over sine squared plus b squared, so long as S is greater than 0. You guys following okay? All right.
Yeah.
All right. I know this isn't very sexy. We're just doing, it's just, you know, using a definition, but you do have to know how to do it.
And for our answers, we're always going to include that domain, like S is greater than 0 or less than 0. Like that's part of our solution.
Yeah, they should. So you'll even see it on the transform tables. If you can see that there.
Yeah, got it. Thank you.
Yep. All right. Let's do one that's a little more interesting. Now, this is a piecewise function, kind of like the valve feeder G function that we were working with. So, yeah, even it's undefined at like 5 and 10 and at 0. So, but we can still evaluate this thing. So let's do it. So what we'll do is we'll plug it right in here in our definition. The problem is it's piecewise, but actually it's not a problem if you know how integration works. If you remember integration, you can split it across whatever interval you want. So what we'll do is we'll break this up into 3 integrals. We'll do one here, and one here. Okay, so on the first interval, 0 to 5, we'll use a 2. And on the second interval from 5 to 10, we'll use a 0. And on the third interval from 10 to infinity, we'll use an e to the 4t. And right off the bat, you can see that this one drops out because of that 0. All right, so now we're down to 2 integrals. One of them's improper and the other one's proper. This one's pretty straightforward. It's just a substitution. Evaluate from 0 to 5, and this is what you'll get. Now for the other one, this one's not bad either, but make sure it's written nicely, and then just use a substitution and evaluate, and this is what you'll get. All right. All right, so now we want to look at the possible S values, right? S is, we're assuming, is in the real numbers, but we all know it's really complex, but it works for now. So let's break this up at S equals 4. So if S equals 4, we have a problem because these guys are 0, so that's not going to work at all. The whole thing is undefined, so that's not in our domain. S less than 4, we also have a problem because if S is less than 4, let's see, that S right there is 3 is negative positive. This is going to turn that exponent's going to positive infinity. So it's going to cause this to blow up to infinity, which means the whole thing is ruined. The only one that works is S greater than 4. So what will happen here is this guy will go to 0. That's just a constant as far as the limit's concerned. There's no ends in there. So what'll happen is you'll just be left with that guy. So there we go. All right, so there it is. There's our Laplace transform. It's valid so long as S is greater than 4. Now here's the interesting part. We transformed a function which is piecewise in the t domain, but when we applied the transform to it, we got this other function, capital F of S, right? But you notice this one's not piecewise, right? I'm sorry, it's not piecewise. It's there's no pieces. Let's put it that way. It's a continuous function. So what happened here is we basically wiped out the discontinuities. We had some discontinuities at 5 and 10, and they get wiped out. That's one of the advantages of using the Laplace transform. It's what made the last problem in section 7.1 worth it. It kind of wiped them out, killed them. And we'll talk more about that in section 7.6. And I'll actually have you do one of these in discussions. We'll do a valve feeder problem on your own. All right, so we built up a few of these. Let's talk about another property of the transform, and that's the fact that the transform is linear. It's a linear operator. So for you mathematicians and engineers, linear operator means the same in every class. It basically means you can push the operator through sums, like so, and it means you can push the operator through constant multiples, like so. And I already mentioned this before, but the derivative is a linear operator. The integral is a linear operator. Linear operators have nice properties that make them easier to work with. Okay. So let's look at an example. So we can exploit that. We can use that to our advantage. So let's say that we have a much more complicated function in the t domain that we want to transform into the S domain. All right, this looks a lot more complicated. I definitely don't want to plug this into the definition like we did in the first 4 examples. But what we can do is we can exploit the nature of the fact that it's a linear operator. We can basically push the operator through the sums and differences and constant and the multiples in front of the constants, in front of the functions. So we can jump right down here to start. You notice that I'm going to push it to the 11. I'm going to push it to the 5e to the 4t. I'm going to push it to the 6 sine 2t. Now, all of them have constants sitting in front of them, so we can push them through the constants too. Like the 6, I can pull it right outside. The 5, I can pull it right outside. And even the 11, I can pull right outside if I leave the inside one as a 1. And now if you look at every single one of these, we did that in example 1. We did that in example 2, I think. And we did that in example 3. We used a B there, but just replace the B with the 2. Okay, so there we go. There's our transform. Now the question is, what about the domain? We've got 3 different ones. 3 different transforms we're applying. Here's the 3 of them right here. So somehow you have to figure out what the proper domain is. And it's actually really easy to do. You just take the domain that's in common to all of them. All right, so this one's valid s greater than 0, this one s greater than 4, that one s greater than 0. So the only way all 3 of them are valid is if s is greater than 4. You guys following okay? Okay. All right, so now let's finally take a look at a table here. This is kind of like the minimum table that you would see in a differential equations class. We're gonna have, there's a more elaborate table that you're gonna want to work with for some of your problems, but this is at the very basic level. So if you go on our Canvas homepage into the resources module, you'll find a larger table, and you'll be allowed to use one on your final exam.
Quick question.
Yeah.
So on the homework, you said that we can't use the table.
Not for this section. This section is all about definitions.
Okay.
Yeah, and unless it specifically says use the table, but you know how you can tell the difference? It'll say in the problem statement, it'll say use the definition.
Okay, gotcha.
Thank you. If it doesn't say that, then you can use the table. Yeah. All right, so what we're going to do now is look at a couple of these we've done already. We did 1, we did e to the at, we did sine bt. And then the rest of them, given enough time, you guys could work through all of these and prove all of these yourself. So let's investigate the table for a minute. So we're going to be working with this table a lot. And the problem with the transform is it doesn't feel very intuitive. Like it's taking these functions into the S world or S domain. But it's not, I don't really see much going on that I can really grab onto intuitively. But what we can see are some patterns. So what I'd like you to do is look for some patterns in there. Look for shifts and look for generalizations. We already talked about one generalization, right? Okay. I'm going to give you a few minutes to look through this. Here, I'll give you another generalization. If you were to choose n equals 0 for this one, you'd have 0 factorial, which is 1. Did you guys know that? 0 factorial is 1. Over s to the first, that's 1 over s. So that's a generalization there. You could try plugging in a 0 for those, for b. You could look at the relationship between maybe this one and that one. This one's got an e, it's got a power function in there. You can see how that comes into a play with this one. So I'm going to give you guys a few minutes to look through this. And then I'll be back, okay? Like 3 or 4 minutes. Come up with all the patterns that you can come up with or generalizations. I'll be right back. All right, do you guys notice some patterns there? A little bit. It's not just a random table, okay? That's all I'm trying to get out of this, okay? If you can notice the patterns, you'll probably be better at catching your mistakes. So like for example, this one right here, when you have a power function in there, t to the n, do you notice that you're going to have a power of s, an increased power of s in the denominator? So look what happens when you put the t to the n and multiply it times e to the at. It takes the e to the at, puts the n factorial on top, and increases the power in the denominator. Or if you take, oh, here's sine bt. If you look at sine bt, and let's see, e to the at, it's kind of a combination of those, right? If you look at this one down here, kind of a combination of both of them. And then same thing with the cosine. It's kind of weird on these two guys down here, they seem to have the same denominator, but their numerators are a little different. Yeah. B and then s minus a matches down there. Okay. All right. And then also notice their domains. Those are going to change depending on where you are. If you notice all the ones that start at 0, let's see, this one, the first one, this one. Let's look at the ones that all have started A. So this one, this one, this one. Do you notice all the ones that start at A, they have an e to the at involved? Okay. All right. So it turns out there's some kind of shift that's happening when you do the transform of e to the at. Okay, we'll talk more about this later. In fact, we'll talk at the end of class today. If you're interested, we'll do the other part of today's discussion, which is optional, and we'll talk about some of that stuff. And hopefully should make this feel a little more intuitive. But let's go ahead and use the table. So let's say that we want to take the Laplace transform of this ugly function, but if you look at the parts and use the fact that L is a linear function, we can push it through everything to break it down into these guys over here. And then we can just use the transform table. And then of course, for the domain, we'd have to look at the common domain for all of our parts. So for example, on this one, I'd push the transform through the constants and sums and differences to look like so. And then we just have to evaluate that transform in this one. And this comes down to just using the table. Both of those are in the table. On this one, you have an n value of 2, an a value of -3. And on this one over here, you have a value of 12 and a b value of 8. And you just plug them in. And there's your transform. Is that okay? It's much easier than by definition. Okay. So yeah, there'll be some problems where they just have you use the table. All right, so not all functions have transforms though. So this part is basically, we're going to talk about the conditions required on the function f of t that will ensure the function has a transform. It would be nice to just look at a function and tell without having to go through and do the limit and show that something goes off to infinity or something. So, so that's what we're going to talk about now. It turns out there's two things that are required for a function f to have a transform. And one of them is the function needs to be piecewise continuous. You guys know what that means? You guys know what continuous means, right? You can draw it with a pencil from left to right. Piecewise continuous basically means you can draw it with your pencil, lifting up your pencil. If you ever come to like a hole, you can lift up your pencil and put it right back down, maybe a little bit above, maybe a little below, but it can't be an infinite jump. Okay, so we'll talk about what I mean by those. But as long as you can do that, go up here, keep drawing, go down here, keep drawing, it's considered piecewise continuous. It's going to have discontinuities that are of a certain type. And the other thing is it has to be, the function f has to be of exponential order. Essentially, this puts a bound on how fast it can grow. If the function grows too fast, then it's not going to have a Laplace transform. Okay, so let's review this. This part shouldn't be so bad. I went through in detail and went through all the limit stuff, but I'm going to let you guys read that on your own. I'm going to give you kind of the general idea, but you try and read through it. Hopefully you remember this from Calc 1, and then we'll go through and we'll define that part, exponential order. So let's start with piecewise continuity. So before we talk about piecewise continuity, you have to know what a jump discontinuity is. So basically you have a jump discontinuity at a point in an interval if the left and right hand limits exist. And they have to be numbers. They have to be finite numbers. They can't be infinity is what I'm saying, right? And then if it's at the end point, you just have to make sure that either the left or the right limits exist. Okay, so those are called jump discontinuities, sometimes called finite jump discontinuities. Here's an example of a function that has some jump discontinuities. Okay. All right. So let's start over here today, and let's draw our pencil from left to right. Draw with our pencil from left to right. So as I move from A over to this point, we definitely have a discontinuity there because you have to lift up your pencil to draw it. Okay, but we only have to lift up our pencil and move a finite distance. And then we're back to where we started. We can jump back down again and continue. So we're fine there. T1 is a jump discontinuity. Now at T2, we have an issue because what happens here is we go off to infinity. So whenever you cross a vertical asymptote like this, we would call this type of discontinuity, we'd call it an infinite jump discontinuity. Okay, even if they're on the same side, even if it was up here, it's still an infinite jump discontinuity if you cross a vertical asymptote. Okay, so, okay, let's say that we pick up over here and let's keep going down. And we've definitely got a discontinuity there because we can't draw it anymore. And then we jump up, so that's a jump discontinuity. And then we go right over here to the edge. Now, this point over here is also a jump discontinuity. If you're on the endpoints, all that has to happen is the limit has to exist. In fact, that's generally what it means for all of these to exist. If the left and right hand limits exist as finite numbers, you have a jump discontinuity. If they don't, then you have an infinite jump discontinuity like so. Is that okay? All right. So finally, what does it mean to be piecewise continuous? Let's say on a finite interval A to B. All that means is if there's any discontinuities, if there are any, there's a finite number and they're all jump discontinuities. They're all finite jump discontinuities. So for example, this guy's piecewise continuous on the closed interval A to B. I don't see any vertical asymptotes in there. It's definitely not continuous, but I said piecewise continuous, right? So it's continuous on pieces. This piece, that piece, that piece, that piece, and that piece. Is that okay? All right. So for our theorem, though, we want to go off to infinity, right? So the only difference between a finite interval and an infinite interval like that is you just change the you just let n go to infinity. So it's the same picture. Just make sure that you only have finite, or what we call more simply jump discontinuities. Okay, no vertical asymptotes. That's the idea. All right, so let's look at an example. So here's a function. It's a piecewise function. We're going to show that this function is piecewise continuous on the interval 0 to 3. Okay, there's the graph. It seems fairly obvious from the graph that it's piecewise continuous on 0 to 3, including 0 and including 3. That's an open dot there. That's okay. And that's a closed dot there. That's okay. All right. So if you look at the graph, clearly we don't have any issues in the middle, right? 0 to 1 is continuous, 1 to 2 is continuous, and 2 to 3 is continuous, including that endpoint over there. Oh, I should put this one in too. Okay, and we can even see it in the functions, right? They're all continuous inside of those intervals. So what we need to do is check the endpoints though. So if we check over here on the left one, if you take the limit, it exists, the limit 0, so it's a finite jump. If we take a look at 1, so we did 0. If you take a look at 1, the left and right hand limits exist, so it's a jump. And if you take a look at 2, the left and right hand limits exist, so it's a jump. And if you take a look at 3, well, we don't need to look at 3, but it's also a jump. Actually, it doesn't even have a jump. All right, so yeah, so this thing's piecewise continuous on 0 to 3. All right, I think you have some questions on piecewise continuity in your homework. Okay. And finally, oh, okay, so more on piecewise continuity. Okay, so let's take a look at this function. Now, if you look at that function, that's definitely a piecewise continuous function, right? In fact, it's continuous, definitely, right? You guys could graph that function. It's a continuous curve. So I don't think we need to go through and prove it's piecewise continuous or anything like that. Did I skip example 8? Oh, here it is. I'm sorry, I skipped something. All right, let's see this one. What about 1 over t? We're going to determine whether it's piecewise continuous on 0 to infinity, including 0. All right, and then without the theorem, we're going to show why its Laplace transform doesn't exist. So let's first check piecewise continuity. So it's pretty clearly continuous everywhere. The only point in contention would be right here at 0. Okay, so really that's the only point you have to check. So we'll just check the left limit. Or I guess you'd call that the right-hand limit, right? So we just take the limit as t goes to 0 from the right, 1 over t. That clearly goes to infinity. Therefore, it's got an infinite jump discontinuity at 0, which means a vertical asymptote, which means that the function is not piecewise continuous on the entire interval. It almost is. It's just there's a problem at 0. Is that okay? All right. All right. So now back to this other one. What about this function? You know, that one's definitely piecewise continuous. It's continuous, so it's piecewise continuous. But the problem here is when you evaluate the transform, like if you plug it in, like we did earlier, and then you work it out, you'll get to this guy here. And then what you'll notice is this guy goes to infinity. So the function that you're integrating over, it gets larger and larger, which means the improper integral isn't going to exist because it's got way too much area. So that thing has no chance at existing. So that means the Laplace transform doesn't exist. So something's happening here because it's definitely piecewise continuous, which was one of the conditions that we need, right? We need, where is it? We need piecewise continuity, but that's not enough, right? The function also has to not grow very fast. This one's growing too fast. Okay, so we have to somehow figure out, well, exactly how fast can our function grow? And this is where we talk about exponential order. As long as we can get it capped, then we can ensure that the transform exists. So let's talk about exponential order next. So piecewise continuity we got down. Exponential order. So a function is said to be of exponential order alpha if there exists positive constants t and m such that the magnitude of the function is less than basically this constant, a constant times an exponential function, e to the alpha t. That's our bound. Okay, if you can find a bound, if you can find an m, a capital M constant, and an alpha constant such that the function is trapped below that, that's enough to ensure that the function is of exponential order. This basically means that it can't grow faster than this guy. Okay, so let's look at an example. All right, so let's talk about both piecewise continuity and exponential order. Yeah, this is definitely piecewise continuous. It's continuous. All right, now is it of exponential order? In other words, is it capped? So what does your gut tell you about this thing? Do you think it's capped? Do you think you can find a function of this form so that this never goes above it? Yeah, it looks to be capped. I mean, the sign's oscillating between -1 and 1, right? And then the e to the 5t, I think that's going to be our cap right there. So yeah, so that's what we're going to do. Look, the cap, you could choose this one. You could choose m equals 1. There's a 1 there. And then alpha equals 5. And clearly, because of the sign, it just oscillates. So yeah, that thing's definitely capped. So what this means, because we've got piecewise continuous and we have of exponential order, it means that the transform exists. We're guaranteed it exists. Doesn't tell us what it is, but we know it exists. Is that okay? All right. And lastly, let's take a look at this one. It's definitely piecewise continuous. Is it of exponential order? Well, the problem with this one we saw above is it grows too fast. The problem is, if that was a t, it wouldn't be a big deal. But the fact that it's a t squared causes it to grow too fast. So what you'd want to do is check, take its magnitude, which is positive. See if you can come up with an m and an alpha such that it's bounded above by it. And you can't really do it. You can't come up with a single number alpha to plug in and a single number m to plug in that would trap this for all of time. If you want to show it, little trick, you can just take this guy. You can divide both sides by e to the alpha t, and then take the limit as t goes to infinity. And what you'll notice is that this quotient goes to infinity, which means you have infinity less than or equal to m. So there's no finite m that'll do that. Okay, so that's a way to prove it if you wanted to. Yeah, and so in this case, the Laplace transform doesn't exist. In fact, we proved it just a few moments ago above. We went through and tried to do it, and we saw that it blew up. So that's not going to work. All right, so in conclusion, most of the problems that we're going to solve moving forward are linear with constant coefficients. So, and the solutions to these, if you remember from chapter 4, are basically polynomials, combinations of polynomials, exponentials, sines, and cosines. And those are all in our transform table. All of those functions are piecewise continuous and they're of exponential order. So we're kind of expecting that all of their Laplace transforms will exist. Okay, so we basically solidified the fact that pretty much all the problems we're going to work with, we can apply the Laplace transform to. All right, let me